Rate law expression. Well, this lecture is divided into two parts. In the first part, we will learn the complete concept of rate law expression. In the second part, we will learn numerical problems of rate law expression. I will teach you my personal tricks to solve any numerical problem of rate law expression. I challenge you that you will not find these tricks anywhere. If you just want to learn numerical problems, then skip the concept part of this lecture. So watch this lecture till the end and you will learn something awesome. Firstly, let me discuss rate of a reaction. In the previous lecture, we learned all about rate of a reaction. If you want to learn about rate of a reaction, watch our lecture and its link is given in the description. Now consider this reaction. We know that the rate of this reaction is equal to minus change in concentration of nitrogen gas upon change in time is equal to minus change in concentration of hydrogen gas upon change in time is equal to plus change in concentration of ammonia gas upon change in time. Using this expression, we can easily find the rate of a reaction. Remember that in this expression, we need both the concentration of reactants and the concentration of products to find rate of a reaction. For instance, we need the concentration of nitrogen gas or hydrogen gas or the concentration of ammonia gas to find rate of a reaction. Thus, in the first method, we learn that if the concentration of reactants and products is known, we can easily find the rate of a reaction. Now there is a second method to calculate rate of a reaction. This second method is known as rate law expression. In this method, two scientists, Goldberg and Weg, use the concentration of only reactants to find the rate of a reaction. For example, consider this general reaction. Now Goldberg and Weg are only interested in the concentration of reactants. They do not consider the concentration of products. We know that the concentration of first reactant is square bracket A and the concentration of second reactant is square bracket B. This small a is the stoichiometric coefficient of A and this small b is the stoichiometric coefficient of B. Now listen carefully. Goldberg and Weg states that rate of reaction is directly proportional to the product of concentration of reactants with each term is raised to some power. Mathematically, I write the concentration of a reactant, the stoichiometric coefficient of a reactant is raised to its power. I write the concentration of B, the stoichiometric coefficient of B reactant is raised to its power. Now to eliminate the sign of proportionality, we need to put some sort of constant. I write rate of a reaction is equal to K into concentration of A raised to its stoichiometric coefficient into concentration of B raised to its stoichiometric coefficient. This equation is known as rate law expression. Remember that instead of this ROR, I will write R in this whole lecture for rate of reaction. Hence note it down this rate law expression. Now consider these reactions and write rate law expressions for them. Well, rate of reaction is equal to K into the concentration of first reactant, which is hydrogen gas. The stoichiometric coefficient of hydrogen gas is 1. We do not write 1 as a power. Into the concentration of second reactant, which is bromine gas. The stoichiometric coefficient of bromine gas is also 1, and we do not write it as a power. Thus, this is the rate law expression of this reaction. Using this rate law expression, we can easily calculate the rate of a reaction. Secondly, rate of reaction is equal to Kn to the concentration of first reactant, which is nitrogen gas, and its stoichiometric coefficient is 1, and to the concentration of second reactant, which is hydrogen gas, and its stoichiometric coefficient is 3. So I write here 3 as the power. Thus this is the rate law expression of this reaction. Using this rate law expression, we can easily find the rate of a reaction. Now let me teach you the most important concept of the rate law expression. Rate law expression is experimental concept, not a theoretical concept. I mean, it is purely based on experiments. It is not theoretically true every time. For example, we will write theoretical rate law expression and experimental rate law expression for these three reactions. In case of this reaction, the theoretical rate law expression is a rate of a reaction is equal to K into concentration of PCl3 and to concentration of Cl2. While in the experiment, the rate law expression is R is equal to K and to concentration of PCl3 and to concentration of chlorine gas. Thus, for this reaction, both the theoretical and experimental expression are 100% correct. Secondly, in case of this reaction, the theoretical rate law expression R is equal to K into concentration of hydrogen peroxide. The stoichiometric coefficient is 2. I put 2 as a power. While the experimental rate law expression R is equal to K into concentration of hydrogen peroxide, and the power is not equal to its stoichiometric coefficient. It is always 1. Here, this is a big problem. I mean, everything is alright, but the powers are different. Theoretically, the power is 2, while experimentally, the power is 1. Thus, we learned very important point from this example. The power are not always equal to stoichiometric coefficient. Let me repeat it. The powers are not always equal to stoichiometric coefficient. So theoretically, this is wrong rate law expression, while experimentally, this is right rate law expression. Similarly, in this case, theoretically, we write R is equal to K and to concentration of NO, the power is 2, and to the concentration of O2, the power is 1. While experimentally, we write R is equal to K into concentration of NO, the power is 1, and to concentration of O2, the power is 2. The powers are different in theoretical expression and experimental expression. So theoretical expression is 100% wrong, while experimental expression of rate law is 100% right. In conclusion, we learned two important lessons in this slide. Firstly, we learned that rate law expression is purely experimental concept. Secondly, we learned that powers are not always equal to stoichiometric coefficient. Thus noted down these two important points. Now here is one important question. How can we solve the problems of powers? Well, the simple answer is to change the stoichiometric coefficient. For example, consider this general reaction. We know that its R is equal to K and to concentration of A raised to the power of stoichiometric coefficient and to concentration of B raised to its stoichiometric coefficient. Now there is confusion in this rate law expression. There is 50% probability that it may be true, and there is also 50% probability that it may be wrong. In order to remove this confusion, here we present a solution. We write R is equal to K and to concentration of A raised to the power X and to concentration of B raised to the power Y. It means that x may be equal to stoichiometric coefficient or it may not be equal to stoichiometric coefficient. Similarly, may be equal to stoichiometric coefficient or may not be equal to stoichiometric coefficient. This is the complete form of rate law expression which we will use to calculate any numerical problem. Remember that R is the rate of a reaction, K is rate constant or velocity constant, X is the order of a reaction with respect to A, Y is the order of a reaction with respect to B. Here, N is the overall order of a reaction and it is equal to X plus Y. Also remember that X, Y are experimentally determined. Secondly, they may be negative, 0 or positive. Thirdly, X and Y are equal to stoichiometric coefficient only if reaction is one step or single step. Thus note down all these important points. Now we will find the unit of rate constant K. Well, consider this general reaction. We know that its rate of a reaction is equal to K into concentration of A, the power is X, into concentration of B, the power is Y. We know that K is the rate constant and we are interested to find its unit. I rearrange this equation. I get K is equal to R upon concentration of A, its power is X, into concentration of B, its power is Y. I write K is equal to the unit of rate of reaction is mole per liter per second. Remember that I write per second outside upon the unit of concentration is mole per liter into the unit of concentration is again mole per liter. I write mole per liter per second upon the bases mole per liter are the same, then the powers X and Y are added. I write mole per liter, the power is X plus Y. I write K is equal to mole per liter, the power is 1 N2 per second. Upon mole per liter, we know that X plus Y is equal to N. I write here N. This mole per liter and mole per liter have the same base. I write K is equal to mole per liter raised to the power 1 minus N N2 per second. This is the unit of rate constant or velocity constant. You must memorize this unit because we will play with it during numerical problems. Also remember these three important points about rate constant. It only depends on temperature. Secondly, if the value of rate constant is high, the reaction is fast. Thirdly, different reactions have different values of K. Thus note down all these important points. Now we will learn the values of K for different orders of reaction. We know that when N is equal to 0, it is a zero order reaction. What about its unit of K? Well, we know that the unit of K is mole per liter raised to the power 1 minus N per second. Here, the value of N is 0. I write here 0. After calculation, I get mole per liter per second. Secondly, when N is equal to 1, it is first order reaction. I write mole per liter raised to the power 1 minus N per second. Here, the value of N is 1. After calculation, I get per second. Thirdly, when N is equal to 2, it is a second order reaction. I write mole per liter raised to the power 1 minus 2 per second. After calculation, I get per liter raised to the power minus 1 per second. Thus using this simple method, we can easily calculate the unit of K for different order of reactions. Remember that different reactions have different values of K. For example, in case of the zero order reaction, the unit of K is mole per liter per second, while in the first order reaction, the unit of K is only per second. Hence, note down this very important concept. So this was all about the first part of this lecture, and we learned the basic concept of rate law expression. Now we will start the numerical part of this lecture. Firstly, let me teach you first type numerical problems. In this type of numerical problems, the unit of rate constant is given, and we have to find the order of a reaction from it. For example, consider these numerical problems. Now I will teach you my personal trick, which is 1 minus n, to solve these all numerical problems in seconds. In the first numerical problem, the unit of rate constant is liter per mole per second. Now listen carefully. I take only mole and its power. Here, the power of mole is -1. I write n is equal to -1. Now I use this formula of the trick 1 minus n. We know that the value of n is equal to -1. I plug in the value of n in this expression. I write 1 minus n to -1. After calculation, I get 2. Hence, the order of this reaction is 2. Thus, knowing the power of mole and putting it in 1 minus n, we can instantly find the order of a reaction. In the second numerical problem, I write mole. We can see that its power is -1. Remember that we do not consider or deal with other values. We are only interested in the power of mole. According to the trick, I write 1 minus n or 1 minus n to -1 because the power of mole is -1. After calculation, I get -2. So the order of this reaction is also -2. Thirdly, I write mole and its power is -2. According to the trick, I write 1 minus n or 1 minus n to -2. After calculation, I get 3. So the order of this reaction is 3. Fourthly, I write mole. We can see that there is no mole present in the unit of K, so its power is 0. According to the trick, I write 1 minus n. The value of n is equal to 0. I write 1 minus 0 is equal to 1. Hence, the order of this reaction is 1, or it is first order reaction. Thus, using this simple trick, we can easily calculate the order of a reaction from the value of rate constant. Hence, note down all these numerical problems. Now let me teach you type 2 forms of numerical problems. In these types of numerical problems, we will learn the concentration chains. For example, consider this numerical problem. For the reaction 2A plus 4B forms products, the rate of a reaction is equal to K into concentration of A, the power is 1, and to concentration of B, the power is 2. What is the effect on rate of reaction when concentration of A is doubled? When concentration of B is halved? Concentration of both A and B is doubled, and volume of container decreases 3 times. Well, the rate of a reaction is already given in such type of numerical problems. I write it here. Now in the first part, we are asked to find the effect of concentration on rate of a reaction when concentration of A is doubled. I write concentration of A changes and it becomes double, or 2A. Now I will use my personal trick to solve type 2 numerical problems. The trick is R dash is equal to change in concentration into R. I write R dash is equal to the change in concentration is 2A. According to the given rate of reaction, the value of x or the power of A is 1. I write here 1 into R. After calculation, I get R dash is equal to 2 into concentration of A into R. Thus rate of reaction increases 2 times when the concentration of A is doubled. Now in the B part, the concentration of B changes. It is halved or it is 1 by 2. According to my trick, I write R dash is equal to the change in concentration is 1 by 2 into B. According to the given rate of reaction, the value of y or the power of B is 2 into R. After calculation, I get R dash is equal to 1 by 4 into concentration of B, the power is 2 into R. Thus rate of reaction decreases 4 times when concentration of B is halved. In the C part, the concentration of both A and B is doubled, or it is 2A and 2B. I write R dash is equal to 2 times concentration of A, the power is 1, into 2 times concentration of B, the power is 2, into R. After calculation, I get this result. Thus the rate of reaction increases 8 times when the concentration of both A and B is doubled. In the D part, the volume of container decreases 3 times. Remember that there is inverse relationship between volume and concentration. When volume decreases 3 times, concentration increases 3 times, due to which concentration of both A and B increases 3 times. I write R dash is equal to 3 times of concentration of A, the power is 1, into 3 times concentration of B, the power is 2, into R. After calculation, I get this result. Thus rate of reaction increases 27 times when volume of the container decreases 3 times. Therefore, using my personal trick, you can instantly solve type 2 numerical problems. Now we will learn type 3 numerical problems. In these types of numerical problems, the rate of reaction increases or decreases. For example, consider this numerical problem. For this reaction, when the concentration of A is doubled, rate of reaction increases 2 times. When the concentration of both A and B is doubled, rate of reaction increases 8 times. Now write the rate law expression and find the order of a reaction. Well, I will always write 3 equations for such type of numerical problems. Firstly, I will write a general rate of a reaction for it. According to the reaction, the rate of a reaction is equal to K and to concentration of A, the power is X, and to concentration of B, the power is Y. Secondly, according to the given statement, when concentration of A alone is doubled, rate of a reaction increases 2 times. I write K is equal to 2 times of concentration of A, power is X, and to concentration of B, power is Y, is equal to 2 times R. It means that if we increase the concentration of A alone 2 times, the rate of a reaction increases 2 times. Thirdly, according to the given statement, when concentration of both A and B is doubled, rate of a reaction increases 8 times. I write K is equal to 2 times concentration of A, X, and to 2 times concentration of B raised to the power Y is equal to 8R. It means that if we increase the concentration of both A and B 2 times, rate of a reaction will increase 8 times. Now in the A part, we are asked to find the rate law expression. In order to find the rate law expression, we need to find the value of X and Y. To do so, I will use my personal trick. I write step 1 and step 2. In the first step, I divide equation 2 by equation 1. My personal trick is I will write only the numerical values in each equation. Let me repeat it. I will write only the numerical values in each equation. For example, in the second equation, the first numerical value is 2r. I write 2r is equal to the second numerical value is 2a and its power is x. I write only 2 and its power is x. These are the numerical values of equation 2. In case of equation 1, I only take the rate of reaction or only r and I divide equation 2 by r. Now this r and this r are cancelled out. I get 2 is equal to 2 raised to the power x. We know that when bases are the same, powers are the same. So x is equal to 1. Thus we have successfully calculated the value of x in the first step. In the second step, I divide equation number 3 by equation number 1. According to the trick, I only take the numerical values. In the third equation, the first numerical value is 8r. I write 8r. The second numerical value is 2 and its power is x. The third numerical value is also 2 but its power is y. These are the numerical values of equation number 3. In case of equation number 1, I always take only r or rate of a reaction. And I divide equation number 3 by 8. Now this r and this r are cancelled out. I get 8 is equal to 2 raised to the power x and 2 raised to the power y. Or we can also write 2 raised to the power 3 is equal to 2 raised to the power x plus y. The bases are the same, so powers are the same. I get x plus y is equal to 3. We already know that x is equal to 1. I put the value of x in this equation. 1 plus y is equal to 3 or y is equal to 2. Thus we find the values of x and y. Now I take the first equation. I write rate of reaction is equal to k into concentration of A, the power is x, and to concentration of B, the power is y. I put the values of x and y and I get this result. This is the rate law expression for this reaction. Now in the B part, we are asked to find the order of a reaction. We know that overall order of a reaction is n, which is equal to x plus y, or n is equal to the value of x is 1 and that of y is 2. I get n is equal to 3. So the order of this reaction is 3. Thus I used my personal trick and I cracked this numerical problem. Now I will show you the power of this trick to solve JEE main question. Consider this MCQs. For the reaction, when the concentration of both A and B becomes double, the rate of a reaction increases from 0.3 mole per liter per second to 2.4 mole per liter per second. When the concentration of only A is doubled, the rate of a reaction increases from 0.3 mole per liter per second to 0.6 mole per liter per second. Choose the correct option. Well, we already know that this question is type 3 numerical problem. So I will write 3 equations for it. We can see that in both cases, the rate of a reaction increases from 0.3 mole per liter per second. So the initial rate of the reaction is 0.3 mole per liter per second. Let me repeat it. The initial rate of the reaction is 0.3 mole per liter per second. I write 0.3 is equal to K and to concentration of A raised to the power X and to concentration of B raised to the power Y. Secondly, according to the given statement, when concentration of both A and B becomes double, rate increases from 0.3 to 2.4. I write 2.4 is equal to K into 2 times concentration of A raised to the power X and to 2 times concentration of B raised to the power Y. Thirdly, according to the given statement, when the concentration of only A is doubled, the rate of reaction increases from 0.3 to 0.6. I write 0.6 is equal to K into 2 times concentration of A raised to the power X and to concentration of B raised to the power Y. Now, according to my trick, I will follow two steps. In the first step, I divide equation 2 by equation number 1. In the equation 2, the numerical values are 2.4, 2x and 2y. I write 2.4 is equal to 2 raised to the power x and to 2 raised to the power y. In the equation 1, the numerical value is only 0.3. I divide equation number 2 by 8. After calculation, I get 8 is equal to 2 raised to the power x plus y, or I get x plus y is equal to 3. In the second step, I divide equation 3 by equation number 1. In the third equation, the numerical values are 0.6 and 2 raised to the power x. I write 0.6 is equal to 2 raised to the power x. While in the first equation, the numerical value is only 0.3. I divide equation 3 by 0.3. After calculation, I get 2 is equal to 2x, or x is equal to 1. We have already calculated that x plus y is equal to 3. I put value of x in it. I get y is equal to 2. Thus the value of x is 1 and that of y is 2. I take first equation. I write 0.3 is equal to K and to the concentration of A, the power is 1, and to the concentration of B, the power is 2. Hence the rate of reaction with respect to A is 1 and the rate of reaction with respect to B is 2. Thus the correct option is C. Therefore, using this trick, we can easily calculate type 3 numerical problems. Finally, let me teach you type 4 numerical problems. In such type of numerical problems, initial rates or initial concentration of reaction is given to determine the rate law expression. For example, consider this numerical problem. Use the following data to answer the question below. Well, we are given initial values of concentration of nitrogen dioxide and oxygen gas with respective rates. Let the power of nitrogen dioxide is x and that of oxygen gas is y. Now listen carefully. I say 0.025 is smaller value because it is the initial value of NO2. 0.025 is again smaller value while 0.5 is a larger value. Similarly, I say 0.011 is a smaller value because it is initial value of oxygen. 0.022 is a larger value and 0.011 is again a smaller value. Similarly, 3.1 is a smaller value because it is the initial rate. 6.2 is a larger value and 6.2 is again a larger value. In the A part, we are asked to write a rate law expression for the reaction. Firstly, I will find the value of x and y. To find the value of x, I will use my personal trick. I divide smaller value of x by larger value of x is equal to smaller rate of x divided by larger rate of x. Or we just write small divided by large is equal to small divided by large. For example, the smaller value of x is 0.025 and its respective smaller rate is 3.1. I write 0.025 equals to 3.1 into 10 raised to the power minus 4. Secondly, the larger value of x is 0.05 and its respective larger rate is 6.2 into 10 raised to the power minus 4. I write 0.05 equals to 6.2 into 10 raised to the power minus 4. Here, at the left hand side, I take whole power x because these are the values of x. After calculation, I get 0.5 raised to the power x equals to 0.5. Here, bases are the same, so x is equal to 1. Thus, the value of x is 1. Now, to find the value of y, I write smaller value of y and its respective larger rate upon larger value of y and its respective larger rate. Or we can just write smaller divided by large equals to smaller divided by large. We can see that the smaller value of y is 0.011 and its respective smaller rate is 3.1. I write 0.011 equals to 3.1 into 10 raised to the power minus 4. Secondly, the larger value of y is 0.022 and its respective larger rate is 6.2. I write 0.022 and 6.2. Here, at the left hand side, I take whole power y because these are the values of y. After calculation, I get 0.5 raised to the power y is equal to 0.5. The bases are the same, so y is equal to 1. Thus, the value of y is equal to 1. Now, I write r is equal to k into NO2 raised to the power x and to O2 raised to the power y. R is equal to k NO2 raised to the power 1 because the value of x is 1 and to concentration of oxygen raised to the power 1 because the value of y is 1. Thus, this is the rate law expression of this reaction. In the B part, we are asked to find the value of K, a rate constant. Well, to find it, I can take values of either trial. For instance, I take the values of first trial. I write the rate of a reaction is 3.1 equals to K, the concentration of NO2, which is 0.025 and its power is x R1, and to the concentration of O2, which is 0.001 and its power is y R1. After calculation, I get K is equal to 11.27. Thus, the value of rate constant or K is 11.27. In the C part, we are asked to find the order of overall reaction. We know that the order of overall reaction is n, which is equal to x plus 1, or n is equal to 1 plus 1 equals to 2. So the overall order of a reaction is 2. In the D part, we are asked to find unit of K. We already know that unit of K is equal to mole per liter raised to the power 1 minus n per second. Here, the value of n is 2. I put n is equal to 2. After calculation, I get K is equal to mole per liter raised to the power minus 1 per second. Thus, this is the unit of K for this reaction. Therefore, using this trick, we can easily find all parameters of the numerical problem. Now I will show you the power of this trick. I will use this trick to solve JEE main question. For example, consider this MCQs. We will find the rate law expression for this reaction. I write here x and y. As usual, I write smaller value, and larger value. Smaller value, larger value and smaller value. Smaller value and larger value. Now we will find the value of x. We already learned the trick. Small value of x upon larger value of x equals to small rate of x upon larger rate of x. The smaller value of x is 0.1 and its respective smaller rate is 1.2. I write 0.1 equals to 1.2. While the larger value of x is 0.2 and its larger rate is 2.4. I write 0.2 equals to 2.4. At the left hand side, I put x as a whole power. After calculation, I get x is equal to 1. Thus the value of x is 1. Now for the value of y, I use the trick. Smaller value of y upon larger value of y equals to smaller rate upon larger rate. The smaller value of y is 0.1 and its respective smaller rate is 1.2. I write 0.1 equals to 1.2. Now listen carefully. Here is one important point which you must learn. The larger value of y is 0.2. But there is a problem. Its larger value is not present. The larger value of y has smaller rate. Let me repeat it. The larger value of y has smaller rate. So I write 0.2, its rate is not there. I write 0 here. So this whole equation cancelled out. I get y is equal to 0. Hence the rate of a reaction is equal to K into concentration of A raised to the power x into the concentration of B raised to the power y. We know that the value of x is 1 and that of y is 0. I get R is equal to K into concentration of A raised to the power 1. Here N is equal to 1 or it is first order reaction. Thus the correct option is D. Therefore, using these tricks, we can easily crack any numerical problem of rate law expression.